Most working professionals are finding jobs the wrong way. They see a job post and they hit the apply button.
Hello, anyone there?
Yes, sir.
I do not know what is happening. I'm not able to hear anyone. Yeah, so then in that case, see, I'm not able to hear today. I'll just maybe run through the slides. Okay. Can you write in this message which part of the slides you want me to do? Let me share my screen. Yeah, so which week do you want me to teach you today? Can you just write it down? Week 4, okay. So okay, fine. So we'll run through the week 4 slides and then maybe we'll do some assignments, okay? Whatever questions I ask, you have to write the answer in the chat box. Then I can understand. Okay, great, great. Thank you, Nishant. Thank you for cooperating. Yeah, so week 4. Give me 2 minutes. So is my screen visible?
Yes, sir.
Yeah, Nishant, don't speak because I'm not able to hear you, but you can write it down. Yeah, okay. Fine. So today we'll talk about Verilog. Okay. So first of all, this we have to understand why Verilog language is needed at all, right? So just hold on. Yeah. Previously when we used to draw digital circuits, uh, at that time we used to have breadboards. I mean, at least in the first year of BTech, right? We used to have breadboards. We used to put AND gate, NOT gate, and they were all chips. And the moment you connected it, you got some combination logic. Now things become difficult when you started to include more and more chips. Okay? Because first of all, we have to cut down in size because it has to go, it will blow up in size because the number of ICs are more. At the same time, you want the functionality to perform. Okay, but most importantly, you have to, while making big circuits, you have to understand that there are billions of transistors. Okay, it is not possible for us to you know have billions of transistors in a single breadboard. Okay, it will be as large as this room. Okay, and will not be able to debug the circuit even if something goes wrong. Think of, if there are millions of transistors, think of how many watts are there. Okay, how things can go wrong. So designers have come up with this Verilog language, in which what you can do is you can define the digital design in terms of text, and it will automatically make the hardware. Okay, so this is a big thing, in fact, because if you because the moment you understand that, the moment you try to, let's say in your Intel processor there are billions of transistors. Okay, you cannot accommodate all the transistors at one place. You cannot test them. You cannot do a proper designing unless and until you have a flow, unless and until you enable the designers to write the logic in such a way such that the debugging becomes easier and the development becomes easier. So Verilog helps us in those areas where you actually define or design the circuit in terms of text, and then automatically it makes the hardware. Now, this is a very big advantage of doing digital design. Okay, of course, there are in analog design there are Verilog A, which is Verilog analog, but you won't be able to get that kind of um, you know facilities that you get in Verilog digital design. So Verilog is mostly same as C. It is not very much different, but it is only syntactically similar to C. Okay, we have to understand that Verilog actually emulates the parallel processing, because when we are doing things in hardware, everything is parallel. Okay, so at that time, uh, whatever you are doing, but whenever you write a C language, it is mostly for the sequential machine. Okay? So there comes the basic difference between Verilog and C. Okay, and the fundamental difference, which is the most important. But only syntactically it is easier to write Verilog because people already have expertise in C, so it is easier to learn this language. But you have to change the whole mindset and the perspective with which you view the programming language. It is very important, right? With that, we will start. So first of all, this is a hardware description language. Now, what is the need? The need is you do not want to hand design a billion transistor digital logic. Okay, you want to do it in a very sophisticated, in a very smooth way, such that you can, before you deploy it, before you make a chip out of it, or before you put in FPGA, you should be able to test it out, okay, to some degree of accuracy, that yes, if it works in my computer in some way, it should be working with some degree of accuracy or similar or same accuracy in the hardware. Now you have to understand that the Verilog language, when you write in your computer is a sequential machine. Okay, so there are ways in which a parallel programming is run in a sequential machine. Okay, and this is a very important technology that has come, because once you understand that a sequential machine can do a parallel activity, you can do much more than what is expected out of HDL. Okay, you can debug things, you can develop things faster, you can reduce the times, reduce the life cycle or the development cycle of a chip. Okay, and this is the reason right now you can see chips are coming out very faster. Okay, only because yeah, sorry. Yeah. So this is the hardware description language part. Okay. And yes, if you have any questions, I'll in between and I'll see the screen. If you have any question, just write it down. Do you have any questions so far? Okay. Yeah. So we model, represent, and simulate digital hardware. Okay, we not only simulate digital hardware, we actually deploy into a digital hardware with the help of hardware description language. Of course, you need synthesis tool and compilation tool for that, but the basic design is in HDL. So there here two things are there. One is hardware concurrency and this parallel activity flow. Okay, so all these things are modeled in a sequential machine with the help of HDL, hardware description language. And there are two hardware description language. One is VHDL, another one is Verilog. These are the most popular ones. Verilog, VHDL is, Verilog is just the advanced version of VHDL. Most of the cases you use Verilog. You do not use VHDL. I mean, in recent times, people are more focusing on Verilog rather than VHDL. Right? So it is spatial constructs and semantics. We have this edge transition, propagation delays, timing checks. Now that when you are simulating a hardware, you have to take care of all these things, because in hardware, this edges, propagation delays, and timing is all that matters in digital learning, right? So you have to make sure that you incorporate all these features into this language. Okay. So in Verilog HDL, the basic unit is of course module. A module describes the functionality of the design and states the input-output ports of it. So the way you select a module is, whenever you think of any functionality, you first write it down in a module. Now module is like a black box, right? You have input, you have output. From the outside it looks like a black box, but for a designer, it has got input, it has got output, and it does some hardware functionality. Now that functionality can be anything, but importantly, the way you modularize things is whichever is repeatable. For example, a adder is very much repeatable, so you make a module out of adder. Okay. Any questions? No. Okay, fine. So yes. So these are the okay. So they have given the terms of adder only. So this is a module. So module name, it has got port list, it has got variable port declarations, variable declarations, description of behavior, and then you have this example. Okay. So similarly, you define one module half adder. You have A, B, sum, and carry. So these are the input and output ports. So A, B are the inputs, sum, and carry are the outputs. So then you define A, B as input, A, B, output, sum, carry. Okay. And then these are the two data flow statements. Sum equals to A XOR B and carry and B. How we write this, and in whichever way we write this, that is all secondary. Most important thing is because these are all governed by syntax. Okay, there is nothing much to worry about. Right? These things you will learn. Okay? This part. So these are lexical conventions. So the comments, you write single line comment like this. You have another single line comment like this, and then you have this multi-line block comment which looks like this. Okay, so this is almost same as C. Okay, of course in C you have another pair where you have this backslash, which means that the comment continues to the other line, but This is the way you write in Verilog. So in numbers, you can represent decimal number, hex, octal, binary, unsigned in decimal form, size base form, include underlines, plus minus, right? And then string, you can of course introduce string within enclose between quotes on a single line. We'll see, look into all these things. These are all examples, but you will find plenty of these examples in the internet. Then you have this A to Z identifier underscore. So these are small identifiers that are used to represent the very long code. Okay, so strings are limited to 1024 characters. First char of is not a digit. Okay, but believe me, for example, even if you don't remember this, the moment you write something like this, the compiler will throw an error. Okay, so it is not much of a brainer for us to, think before writing, because the moment we write, a compiler will throw error. Once the compiler throws error, you know where it has gone wrong. The problem comes when you do not know where things go wrong. Okay, so, and there are many things which can go wrong when you write a HDL code. These are values and registers. So these are the logic values 0 and 1. So can anyone tell me what is X? Anyone? Correct. And what is Z? Right. So you tell me one thing. So don't care means what? What would be the voltage level? So for example, if I measure don't care, what would be the voltage level? Correct. And for high impedance, what would be the voltage level? No, not true. For high impedance, the resistance is infinite. The voltage level is not infinite. Okay. So the moment, see, in don't care, the moment you put a multiplicator, you get 0 or 1. What what it means is, whether it is 0 or 1, it doesn't matter. Okay. It is in some stable value, but it does not affect your circuit. It doesn't affect your circuit output. Okay. That's what is meant by, don't care. But in high impedance, whatever voltage you put there, it will take that voltage. So whether if it is a pull down, it will take 0. If it is a pull up, it will take 1. So it is up to you how you want to insert the voltage in that high impedance state. Very, very important. Very important. Okay, so yeah, this one. Okay. So in these vectors, you have var 702A. So this is what you are defining, that you have a 8-bit vector, you have a 32-bit address, and then you have this. So you are assigning this 4-bit address out of the 32. You are assigning 4 bits to A. So what it means is the subset can be selected. Okay. Description size. So very important. This structural description. So what it means is, in Verilog, there are ways in which you can define a circuit. Okay, and those are called styles. So you have different styles of representing the same circuit. So let's say that if you have you know, you have this circuit which is there in the front of your screen, you can represent it in different ways, which means is you can write different Verilog codes for the same circuit, and it will generate the same a digital circuit, which does not happen in C. In C, if you change the statement, it might generate a different assembly code. Of course, the functionality remains the same, but the number of instructions can be different, which is not the case with Verilog. Okay, so here you can see, so this is called structural design, where you make the schematic, okay, and then you can associate, you can have all these components. So this is a not component, N1, which is given by not. This is A1, which is given by add. This is A2, which is given by and finally one OR circuit, which is given by O1. Okay, and you are connecting various inputs and outputs. But importantly, what you have to understand is, you know the sequence in which the inputs and outputs are appearing in this description. Okay, without the knowledge of that, it will be very difficult to write a structural design, and most of the time structural design is not followed unless and until there is a legacy design or a legacy component block that is there, right? So right now, data flow design. So in data flow design, you don't have to worry about all these components. It's not and or. So they have transformed
Hello,
these
hello, sir. Hello, sir.
components
One
into
question, sir.
symbols. Okay, so basically it is and, or, not, and. So here you can see that you are not writing any text of not, and, or any other thing. It is just that you are writing uh, one statement, assign output statement, and then you are representing it in the schematic, right? Then you have this behavioral style. Okay, so in behavioral style, what is important is to understand you do not care about the circuit, you care only about the behavior of the design. Okay? So it might happen that we know that any combination logic can be represented in a mux form, basically with the help of multiplexers and with the help of combinational gates, right? So whether you define it in terms of mux or combinational gate, it really doesn't matter. Okay, you will still have this behavioral design. Now you don't have to write the truth table for it. You just have to understand the moment you see the truth table, from there you can write the code. You don't have to make the Carnot map from there, and you don't have to solve the Carnot map to get the design. Right? So in structural modeling, what you have is this execution concurrence, format, primitive gates, and G2 carry AB. First parameter carry out, other inputs AB. Right? So in data flow modeling, you have this assign statement. So in assign statement, these are the building blocks for any data flow modeling. Okay, and of course we will talk about delay, that what is delay and what. So assign sum a equals b means sum is equals to a XOR b. So do you have any questions still here? I guess no.
Hello, sir.
Okay.
Hello, sir.
Jivan, can you please write it down? I'm not able to. The speaker is not working, unfortunately. So if you just
Okay,
write it
sir.
down, then I can, you know,
Okay, sir.
answer the questions. I'll wait for you to write it down. Yes, Jivan, you can write down the question. Sometimes in structural model, you can have input followed by output, but in sometimes you can have output followed by input. That depends on how this legacy nodes are defined. Okay. So it can be output followed by input or input followed by output. Right? Was that okay? Yeah. So Remember on this thing. All continuous assignment statements execute concurrently. Very, very important. Okay. So So order of the statement does not impact the design. Why? Because in see in hardware, let's say you have two AND gates. It really doesn't matter in which whether you are placing the two AND gates side by side or just one above the other. Okay. As long as the inputs are coming, it will function instantaneously. Hmm. So right now you can see that delay can be introduced. So hash to sum A XOR B, what it means is you execute the line after two time units. Okay. Now, how to define the time units? You are defining the time units with this directive. Okay, time scale directive. So this with the two time units, what so it can be like hash 3, hash 4.5. So this time scale is defined in terms of the time unit and time precision. Okay, so the moment you write 1 nanosecond by 100 picoseconds, so 1.23 would mean 1 nanosecond and 23 picoseconds. But the moment you write 1.001, this 0.001 it won't help because sorry, 1.23 it is 100 picoseconds, so it will be considered as 1.2 picoseconds. Okay, because the three part will be absorbed because the precision is lost. So similarly, this 1.001 will be considered as 1 nanosecond. Okay, so keep this thing in mind. Yes, so this time precision is written as yes, so 0.1 second. So 10.512 will be taken as 10.5 nanosecond, right? Very important. And now where to define this time scale directive and all that we'll see as we can as we progress through this slides. Data flow modeling. In data flow modeling, for example, we'll take one simple case. This is one example of data flow modeling. Now remember, data flow modeling means that you do not use the legacy gates, you do not use the structural gates, but you use the XOR and the AND symbols of Verilog. These symbols are provided with Verilog. The moment you use XOR and AND, it will automatically translate to these kind of gates. So what this assigns tree means is once A and B changes, you assign this A and B after 3 nanoseconds. Okay, because hash 3 is 3 nanoseconds. Okay. Similarly, carry is after 6 nanoseconds. Okay. So this is what it means. So you see that after A and B changes, it is only after A changes here, after 3 nanoseconds your sum changes, right? Because B hasn't changed after 3 nanoseconds. And after this, it changes after 6 nanoseconds. Okay, so very important this part, right? That A and B changes, it changes after 6 nanoseconds. So these are called inertial delays. So in behavioral modeling, it looks like this. Module marks 2 cross 1, you have A or B or cell. Okay, so this is the sensitivity list. Now remember, in hardware there is no concept of sensitivity list. It is only in the simulation you are giving for the purpose of simulation that you have A's or B or cell so that they understand. Okay. So A's or B or cell. So sensitivity list. Uh, and then so here the thing is, if cell is equals to 1, out equals to A, and out equals to B. It is a simple mux behavior, right? Just hold on, let me see if there are any questions. Is it true if I'll write XOR A B sum, can I write in this way? Yes, yes, absolutely you can write in this way, no problem. It is just that okay, you have to first, you cannot write in this way. What you have to write is XOR x1 A comma B comma sum, right? So this is the way you have to write. So what it means is that your XOR is the actual gate name, X1 is the instantiation, one component of that XOR. Okay, and A is the input, B is the input, and S is the sum. Okay. Now remember that whenever you are writing like this, you assume that the XOR was defined as input, input, output. Had it been output, input, input, the whole thing would have gone for a toss. Okay, so that's why before you write structural code, it is important. No, it is not mandatory, but essential. Okay, because what happens is, if the moment you write XOR, 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 the compiler will anyways give it a name. Okay, I can give any level name for that. Yes, you can give any level name for that, no problem. But it is important that you name it so that you can keep a track of all the instantiations that you are doing. Or else the compiler will do it for you. But the compiler will definitely give some name to each, or the synthesizer will definitely give a name to all your XOR instantiation if you are not giving them. Okay, Nishant is okay. Jivan, is it okay? Yeah, so we'll proceed. So this is what is XOR. Okay. Then you have this always block, right? Always block means it's a sequential block, and in always block you do uh, this is the way you write a always block. Whenever there is a change in A, B, or cell, this always block gets executed. But most importantly, always block is used to model a flip-flop. Okay, it's very important. Now there are two types of delays. One is the inter-SL statement delay. One is the intra-statement delay. We'll come to it. Okay, so in inter-statement delay, what this means, hash 2 equals to base. So what it means is, after some A's or B's executed, then you exert, you know, you delay the execution of this carry. Now, in intra-segment delay, what you are doing is you calculate A and B, but you assign to carry 2 nanoseconds later. So this is more like transport delay. Okay, so, and this is the same as almost the propagation delay. So after A and B changes, after hash 2, or after 2 nanoseconds, or after 2 picoseconds, whatever is your time directive resolution, based on that you can give to carry, right? So procedural contract. So these are the two procedural constructs. One is the initial statement, one is the always statement. So in initial statement, it executes only once. So what it means is, whenever your classic starts, it executes only once. Okay. That is only one time it will execute, and always statement executes with each loop. What it means is, whenever there is a change in sensitivity list, at that time sum and query will get executed. But for initial, it is just used to initialize the values. Let me see if there is a question. No question, right? Any questions so far? Yeah. So this one, event control. So in event control, what you are doing is, as you can see, pause edge of the clock. What it means is, pause edge means you can see all this thing from 0 to x, or 0 to z, or 0 to 1. Okay, and x to 1 and z to 1. Okay, so these are all called pause edge of the clock. Okay, and then negative edge means just the opposite, 1 to x, 1 to z, and 1 to 0, like that. Okay. So level triggered is A or B whenever there is a change in value. Okay, at that time. So whenever there is a transition, at that time, uh, this is triggered will get triggered, and whenever there is a change in the level. Okay, so for example, whether it goes from 1 to 0 or 0 to 1 does not matter. At that time, level triggered event control will get triggered, right? So this is mostly used for making a latch, and this is mostly used for making a flip flop. Okay, loop statements. So loop statements, repeat, while, and for. So this is the example of a repeat. So in repeat you count if sum equals to sum plus 5. So it is same as writing for I equals to 0, I less than 5, I plus plus, the way you write in C, that you repeat one statement for this many number of times. Okay. So yeah. Any questions? No questions. Okay. So these are the loop statements. In here you see that in loop you do the same thing as repeat. Only thing is you have to increment the count equals to count plus 1, and then in for loop you have to make sure you give something like this. So these are just different syntaxes. I prefer always the for loop because it gives me more control. I am okay to write more number of text, but I want clarity. These are the conditional statements. For example, if this condition is there, then execute this procedure statement. So this is same as having a mux statement, right? Where you get if some condition is there, you execute this, execute this. Okay? So this is the conditional statement. Then you have this case statement. Case statement is very important for modeling a multiplexer, right? And you can see that if the b is 0 0, you get y equals to a is or b, a plus b, or else a minus b, or a this division b. Very very important. Case x and case z. Case z is considered as don't care. Okay. In case x, both x and z are considered as don't care. Okay. So it is like if you have this case z, you have b1z and z will be treated as don't care, but when you have x here, you can write even x here. Okay, still it will work. So very important. Then you have net types and register type. So I think, yeah, let me complete this. So net type and register type. So net type is mostly like var, and register type is x. Okay, so net type is var. Okay, and this is what is most of the time used, and register type is reg time. And see, some things are synthesizable, some things are not synthesizable. Okay. What I mean by synthesizability is, even if you write a Verilog code for this, it doesn't necessarily mean that it will make the proper hardware for those code. Okay. So have to be very very careful of how you write a Verilog code. Okay. So yeah, data types var, this is the format. In var you first write msb lsb var. So basically you define a bus here. So var reset means it is only one var of reset. Clear means there are 7 vars of clear. Okay, so this is the way you write. Okay, restriction on data types. So data flow and structural model can use only var data type, cannot use reg data type, which is absolutely wrong, because you can still use reg data type on the right hand side. Okay, in data flow. I think this presentation is a bit of it has got a mistake. Okay, which was used. Remember this one, right? And behavioral modeling is we can use a reg data type on the left hand side. We cannot use a var data type. We can use a var data type on the right hand side, but not on the left hand side. So, yeah. Questions, any questions? Looks like no questions. Right. Okay. And then you have this compiler directives. Okay, you have this hash defines used to define global parameters. Example, hash define bus width, range, and undef. Okay, so similarly you have this defined bus width and undef bus width. So these are not very much used, so we'll not talk about it much. Okay. Compiler is if you want to use a Verilog file, but most of the time what happens, your tool takes care of this. Okay, you don't have to include separately one Verilog file. It normally takes care of this. So this display task. Okay, so display or monitors are used, to display the variables, internal variables. Okay, and these are not synthesizable. So these are tasks. But what I prefer is to do it in the simulation window, not in the monitor. Okay, simulation control task. You have finish, make the simulation exist, suspend the simulation. Okay, we'll look into it once we do the simulation. Okay, and time is gives the time of the simulation. So this is called port connections, type of port connections. Okay. So the child module. So this is same as doing a structural modeling. Okay. So this is, you have an internal module. The moment you instantiate it on the top module, you have to specify by what input goes to what output, right? Type of port connections. So these are the connections. Okay, connections by name is also fine. So here you say, specifically say that signal C is connected to G3, signal D is connected to G2. This is the way you write. Okay. Here it is implied because you are following some order. Okay, the order has to be same in which you write it. Okay. Empty port connections. So if an empty port is set, port is set to, well, for example, let's say that you have A, B, Y1 and there is an empty port. What it means is out to is basically empty connection. You will not get anything in out to, right? And if the input is not inside, the port is supposed to have high impedance. So test bench is very important. I mean, more see, test bench is like a multimeter, right? You are using a multimeter to test your circuit, but if you have a faulty multimeter, you do not know where it has gone wrong. Okay, so test benches are as good as multimeters. Okay. Very important. So in test bench, what you do is you instantiate your module. Okay, instantiate your module, and then you provide inputs to the module. There are some set defined inputs, and then you check whether you are getting the proper outputs or not. Right? Yeah. So this is like generating stimulus. You generate something like this for clock, but there are other ways in which you can generate a clock. Yeah. So this is another way. Hash carry clock. This. So this is the way you do. Uh, mod z equals to x and mod x equals to x. Yeah. So initial value of the clock invalidated is 0. So you make sure that you initialize it with 0. Okay, that is important. So the correct way to do it is, if you initialize in clock equals to 0, then you use a always begin statement to change this clock. This is almost same as generating this one, right? This one. So yes. So I think this is the end of the. Any questions? We'll try to do some problem solving. Any questions? Okay. Try to solve problem. I think week 4 here is the is very long simulation area delay model. Right. So I think here we missed it out. But in case we'll try to solve whichever is for very long. Okay. Any very long. Acha, can you do question number 3 and tell me? Sum of products. Huh? Can anyone do it? I hope you are able to see the screen, right? Is my screen visible? Hello? Yeah, I have not gone there. I have not gone there. F in and F out. This is fan in and fan out. I have not gone there. uh, we will graph for that this code. We have not spoken about this TP propagation delay, this then fan in and fan out. We'll talk about that once I start. Today it will be only very long. Yeah. So we'll just check this three. Can you do this three? I'll give you 10 minutes. Just do three and tell me. Yeah, I'll open it. I'll open it. Question number three. Just do it. I'll give you 10 minutes to do it. Anyone who would do it? Option A. Okay. So I have not checked. We will check. What is option A? Okay. And question four as well. It is a bit tricky. this question 4. One 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 zero. Let's see. Option one says option 5. Let's see. Option 5 is 1110. So it should 1110. Very good. I think, yeah, that's correct. So 1 2 3 4. So check. Yep, it looks like it's correct. Good. I'm not going into this prime implicants and etc., because these are not very much required. I do not know why this kind of questions are posed. Okay, we'll go to week 4 and we'll try to solve the Verilog questions. Okay? I hope there are Verilog questions. But I guess, yeah, so they're all marked. Okay, so for Verilog, I would suggest that there is something called ASIC world. Okay, so I'll just write it down. ASIC world. So you should see this site for learning Verilog. Okay, don't go through videos, don't go through books. Okay, it really doesn't help. Uh, for programming languages, sites are the best while learning programming language. Yeah. So, yeah. And you had this question, TPFN effort. Let me see, where is this? In can Jivan tell me this TPFN effort? Where is this? In which slide it is? Because I don't have. Let me see. Area delay model. In which slide it will be, so that I can see? Lecture week 4. That's fine, but I do not know. Let me see. Week 4 looks like this one. I'm not able to find. Just hold on. too much. So
a Boolean expression,
let me see.
whatever methods would be the to elaborate that particular notion of cost. And we'll also see whatever methods we have studied, what is the optimality of those methods, or for same Boolean we had defined that a particular expression, the input is a sufficient idea that what would be the area of a particular chip. Now the significant all, so this is how
How this is.
while the input plate, we can also find out the delay of whole expression or whole logic whatever we are implementing. So for one particular gate, these input number of inputs or number how much silicon we are going to consume when we implement a particular expression, and delay is end to end delay. So let's say all the inputs are available when the output gives of output.
See, looks like this. I mean, the slides for this one is not available. So, can anyone tell me the presentation number, or I'll just have a look, and then maybe next week, can Nishant or Jivan, can you remind me of this area delay model? I'll just explain to you after I get a hand on the slides. ठीक है, ठीक है. So I guess today this will be the end of it. We'll again meet on Sunday. If you have any other questions, yeah, please, 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 Jivan, go ahead. Yeah, assignment 4 propagation delay. So let me see the assignment 4. Can you pose the question here? Okay, okay, okay. So yes, maybe then in that case, if it is regarding this TPF and FO, then we can have a, you know, I mean, next Sunday when we sit, just remind me of this. But do remind me, don't forget, because I'll forget. So please remind me about this TPF in an FO. Right? That is important. So yeah, we can end our class today. We can meet on Sunday. If you have any questions on Verilog and all, just let me know. I'll try to answer. Thank you. Yes, Jivan. Yes, you can leave the class. And thank you.